Okay, so first thing, we have quiz 3, I think it is, on Wednesday. What's today, the 29th? 28th. So Wednesday the 30th. And then exam 3. Well, actually, even before that, come on. We're going to do another quiz a week from today. So that is December 5th. And then exam 3 is Friday, December 9th. And the topics for that are everything up through internal loads. And then exam 4 is during our finals period. I'll get you that information. And the topics for that will be everything up through friction. Okay, so that's everything you have left. There will be, I guess, one more homework assignment, regular homework assignment. Any questions about that? I don't know about a weekly one, but there'll be one more daily assignment. Okay, and so now we're back to friction. And that is square threaded screws, belt friction, and bearing friction. And bearing friction is broken up into journal bearings and thrust bearings. We've talked about this, we've talked about this, so now we're going on to bearing friction, and that's the last new stuff we have to talk about in this class. Okay, so bearing friction. And we'll start with journal bearings. And journal bearings, are bearings like axles. Where the thing is rotating some direction, it doesn't matter which. Let's call that the direction of motion. And there's some force being pushed perpendicular to the axis of rotation. Let's say that this force is W over 2, so the total force is W. And mu can be static or kinetic, depending on what type of problem you're trying to solve. And what you're solving is either first, the maximum couple, capital M, that you can apply to the axle. Before rotation starts. In that case, the thing is at rest initially, like when you draw your free body diagram, you're dealing with something that's at rest, and so your coefficient of friction needs to be a static coefficient of friction, which is a bigger value than the kinetic value. And second, you can calculate the couple M that's required to maintain rotation with a constant angular velocity. In that case, when you draw your free body diagram, the thing is rotating, and so your coefficient of friction would be a kinetic coefficient of friction. So if you're given the static and the kinetic coefficients of friction, then you have to use the wording of the problem to figure out which one you're using. But other than that, the math is all exactly the same. Okay, so let's draw a free body diagram. We'll think of it as a side view looking down this end of the axle. And so the free body just looks like this. Here's the center of the axle. I'm going to draw a center line because that's going to be important to all this. And since we're isolating the whole axle, you don't have to worry about dividing it up into two different weights over two. We're dealing with both of them, so we just have a straight weight down. Okay. And the motion is this way. I'm trying to draw that far from the body so you can tell that's not a load on the free body diagram. Okay, so if it's a static coefficient of friction, then it's a static coefficient of friction. Then that really doesn't mean much of anything, actually. So this is you only have to worry about the direction of motion if it's kinetic. But if it's already rotating, that's the direction that it's rotating. Okay, so what happens, like let's think about it, since I already drew the motion thing here. Let's think about what happens as this thing is spinning in its bearing. Well, for this to be in static equilibrium, or equilibrium of any kind, to have no angular acceleration, that W has to be offset by an equal and opposite force. Let me draw that straighter. Okay, so this is also W. Okay. But it's going to be offset. It's not going to be acting like if you measured the profile of the loads, the center of pressure wouldn't be at the bottom of that axle. It would be offset like this. And so if you draw a line here, okay, and think of this angle as theta, notice that in order to figure out the couple that's applied, you have to figure out this moment arm that I'll call rho. Okay, so this is the if you think of this couple M as being equal to rho times W, this is the magnitude of the moment that you have to apply to keep this in equilibrium. Okay, well, what is that weight force made out of? This is where the friction comes into it. That the W, the W coming down is the weight, I guess. This one coming up is a contact force that's equal and opposite. But that contact force is made of two things, a normal force and a friction force, right? The normal force has to be perpendicular to the surface. So it's like this. Try to draw that well. Okay, so there's the normal force. And then the friction force is tangent to the surface, perpendicular to the normal force. And that's equal to mu times the normal force. Okay. And this angle is theta. That's the same angle, theta, as in the center of this axle. And notice that, this is going to come into it, the radius of this axle. So let's call the radius of that axle capital R. Okay, that felt a little hectic. So let's go through what all these things are again, okay? So we know for this to be an equilibrium, for there not to be a vertical acceleration, there has to be a force W, contact force, that counteracts the weight force, right? That has to be the case. That contact force is made up of a normal force and a friction force. Okay, so that's the green and the red here. Okay. The angle between that contact force W and the normal force is the same angle as the angle from the vertical, a vertical line through the center of the axle to where that contact force is applied. Okay. So, and really the final thing that we're trying to figure out is what that rho value is, that distance rho. If we know that rho value, then we can calculate the couple that's required for this to be in equilibrium. Okay. Okay, so how are we going to calculate that rho value? Well, you can see that rho is equal to R times sine of theta. from the triangle that's inside the axis, inside the axle, right? So it's just trigonometry says r sine theta is equal to rho. So we just need an expression for theta, and then we can write this whole thing out. Are you with me on this, or you think this is stupid? Okay, good. Okay, so we're going to use the normal force and friction force triangle to come up with an expression for theta. And then we're going to use that expression in the expression to get rho, you know. So it'll be like, we'll find theta, then rho is equal to r sine theta, and then the couple is equal to rho times w. Okay, so that's our strategy. Okay, so what's the expression for theta? Well, the theta is equal to, notice that the tangent of theta is mu n over n. So let me write that first, I guess. So tangent of theta is mu n over n. And the n's cancel out. So tangent of theta is just equal to mu. And so theta then is equal to the inverse tangent of mu. Well, rho is equal to r times the sine of theta. So we want an expression for the sine of theta. So let's think about this triangle. You know, we have a triangle where this angle is theta. The inverse tangent, or the tangent of theta, is mu. So we can write it like this. You know, we have like mu here and 1 here. We could have written it also as mu n and n. So what's an expression for the hypotenuse of this triangle? What's the length of the hypotenuse? This is going back to SAT stuff. I'll write the answer while you think about it. Well, that's where we're going with it, but you can just use the Pythagorean theorem here. And so based on this, you know, SOHCAHTOA says sine of theta then is just equal to opposite over hypotenuse. So that's mu over square root of 1 plus mu squared. So rho is equal to r times mu over the square root of 1 plus mu squared. And so the couple required for equilibrium is r times mu times w divided by that square root. Okay, any questions about that? So the way this would work is, so let's say that you have so you have a wheel and a bearing here. And another bearing here. And then another wheel. And these are on the ground. And let's say that the force pushing down, half the weight of this vehicle is, let's say, 2,000 newtons. That's a pretty small vehicle, but okay, let's go with that. And let's say that the friction, and I'll say kinetic friction, is 0.05. What couple is required to overcome the bearing friction and maintain a constant speed? Okay, well, in this case, we're going to take one of these two bearings, and that one bearing is going to take half of that weight. So our W is just going to be 1,000. Okay. So free body diagram of 1/2 of the axle. And we have the weight coming down of 1,000. We have the weight also pointing up of 1,000. We have the friction force that's tangent to the surface of the axle. So this is mu times the normal. This one, the green, is the normal. Theta, theta. Okay. We could just plug into the formula at this point, but I want you to just remember how this works. I want you to be able to run through this. I won't be like a super stickler for like how airtight the proof is or whatever, but I want you to remember sort of the big ideas and be able to sort of derive this. So I'm going to do it the other, like you could do it the way I just did it. I'm going to do it in sort of reverse order, but all the ideas are exactly the same. So what we want is this, right? So rho is equal to, oh, and I need to give a radius of this axle. Let's say the radius is 1 centimeter. Okay, so rho is 0.01 times the sine of theta. We have this triangle that says if theta is here, the opposite side is mu n, the adjacent side is n. The hypotenuse is n squared plus mu squared n squared square root. So sine of theta then is opposite over hypotenuse. So mu n over, notice that I can pull an n squared out of both of these. So this is equal to, well, I'll write the extra step. So square root of this, which is mu n over n times the square root of 1 plus mu squared. And you can cancel the n's. So sine of theta is equal to mu over 1 plus mu squared square root. So rho, well, let's get a value for this. So sine theta is equal to 0.05 divided by square root of 1 plus 0.05 squared. Which is 0.04994. So rho is equal to 0.01 times 0.04994. Which is 4.994 times 10 to the minus fourth, and that's meters. And so the couple then is equal to the weight times rho which is 4.994 times 10 to the minus fourth times 1,000, which is 0.4994 Newton meters. So in order to keep this moving with a constant velocity, that's the couple that you have to apply to the wheel. And that's what the engine has to do. Of course, there's other more major sources of friction than that. There's air resistance on the car body, there's rolling resistance, but this is the couple that you have to apply just to overcome the bearing resistance.
Can you use 1000 as the hypotenuse for that?
Yes, 1000. Yes, that also you could use 1000. Yep. So let's see, everything would cancel out, right? Wouldn't it? So you get sine of theta is equal to this over 1000. Yes. You get the same thing. So the bottom line is, feel free to plug values in anywhere along this path. That's fine with me. I just want you to sort of remember how this process works, how these things all relate to each other. Plug in the 1000 here, plug in the 0.05 at the beginning, whatever. That's fine with me. Any questions about that one? Okay, well, that is journal bearings. So now thrust bearings. And a thrust bearing is like this. So if this cylinder is rotating in the direction shown, and you have a force pushing this together, we'll call that W, against a surface, this is just some surface, then the question is the same. This can be a static friction coefficient if you're looking for what couple is required to initiate motion. Or this can be a coefficient of kinetic friction. If you're looking for the couple required to maintain a constant angular velocity. Okay, well, how do you derive this one? So let's look at, think of the surface in contact with the cylinder. So it's a circle. That's not a very good circle. There's that, but I'll live with it. And this thing has a radius R, capital R. Okay. Well, now let's think about an infinitesimal ring around the center. that has a thickness d little r, and it's a distance little r from the center. And the useful thing about this, whenever you're using, so this is going to end up being an integral derivation. And anytime you're doing an integral derivation, the way you break your area or your volume up into increments is kind of the whole game, you know? So I'm breaking it up into these infinitesimal rings because notice that each one of these, so if there's a force, a friction force acting around this ring, okay, every point on this ring is the same distance from the axis of rotation. And so every point on this ring is going to produce the same moment, okay? So all we have to do is figure out the total friction force acting on that ring, okay? So I'm going to do it in these steps. Here's the strategy. First, I'm going to figure out the infinitesimal normal force acting on that ring. And I'll call that little ring dA. Okay, it's our little infinitesimal piece of area. Once we have that, we can figure out the total friction force. So I'll call that d force of friction, because that's just equal to mu times our infinitesimal piece of normal force. And then our infinitesimal piece of moment, so dm, is equal to little r times d force of friction. And then finally, once we have our infinitesimal piece of the moment, our total moment is just the integral from, I'm going to write it as r inside to r outside of dm. So this would be 0 for a solid cylinder, non-zero for a hollow cylinder like a hollow tube. Okay. Okay, so first, the first step is we need to find how much of that normal force is acting on that ring. Okay, well, can you come up with an expression for the area of that infinitesimal ring? This is like the oldest trick in the integral definition book. Imagine slicing that ring. This comes up in so many derivations like this. Slice that ring, stretch it out. It's a long, thin rectangle with a length that's equal to the circumference of that circle and a height that's equal to dr, its thickness. Okay, so dA is equal to So this is like the first step. dA is equal to 2 pi times little r dr. Okay. But what we want to figure out is how much of the normal force this is. Well, notice that the fraction of the normal force is the same as the fraction of this area to the total area. So you can think of it as like d normal force is equal to 2 pi r dr over the total area, which is pi big R squared, times n. Okay, so take a second and look at that and tell me if you follow what I'm doing there. So what I did was I came up with an expression for that infinitesimal area. Then I got the fraction of the total area that's made up by that infinitesimal ring. That's this fraction here. And then I multiplied that by n to come up with, you can think of it as like what I did was dn over n is equal to dA over A. With me on that? So now that we have dn, we can calculate the infinitesimal force of friction. So d force of friction is equal to mu times dn. So d force of friction is equal to, I'm just going to substitute in this expression. So now we have 2 mu n pi r dr over pi r squared. I could have canceled those pi's before, but I didn't because I'm stupid. It's like my dad always said. Okay, so this is equal to 2 mu n little r dr over big R squared. Okay, so that's the force of friction. Okay, so now how do we go from the force of friction to the infinitesimal bit of moment? Well, since that whole infinitesimal area is the same distance r from the axis of rotation, dm is just equal to r times d force of friction. And so dm is equal to 2 mu n r little r squared dr over big R squared. And now all we have to do is integrate. That's our little increment of moment. Now we just need to add all the infinitesimal moments. So the total moment then is the integral from, I'll write it as r inside to r outside. Of 2 mu n r squared dr over big R squared. Most of the stuff we can just pull out. So this is 2 mu n over big R squared times the integral from inside radius to outer radius of little r squared dr. And actually, I am going to notice that, well, this big R is the outer radius, right? So I don't know, you can call that whatever. I'm going to erase all these. Sorry if that messes up your notes. So I'm going to take away all the R outers and just call that big R, and I'm going to leave the R inners. Okay, so now take this integral. M is equal to 2/3 mu n over R squared times little r to the third, evaluated from R inner to R. And that is 2/3 mu normal and this is, I guess I'll have the R squared on the bottom. And then all this is multiplied by big R cubed minus R inner cubed. And so you can write this as, your final expression for the moment is equal to 2/3 mu times the normal times the quantity big R minus R inner cubed over R squared. It simplifies if you know R inner as a function of R. So like if it's half of the outer radius or something, then that formula simplifies. It also simplifies if it's a solid cylinder. So for solid, you just end up with the moment is equal to 2 times mu times what did I call that force? N. So 2 times mu times N times big R divided by 3. I'll do an example with numbers next time, but what you need to remember are just kind of these 4 steps, how to think through that. And you don't have to do it symbolically if you don't want. You can plug in the numbers I give you, but you have to set up that integral, calculate that integral. Question, Alex?
Wasn't the downward force marked as W at the earlier?
Yes. I think you are right.
Yeah, just think about
So that would be, okay. So it's going to be easier if I just change it up here.
Yeah, exactly.
Thank you. So on the final, I'll probably just make you do this derivation for like an angled surface or something. No, just kidding. That would be really mean. But you can imagine how that would be possible, that kind of thing, like using this sort of idea. But we'll do everything just nice and simple, just like this. Either you'll have a solid cylinder or you'll have an inner radius and an outer radius that you know the ratio, and you'll be able to just use this if you drive it. Okay, that's all. Goodbye. Well, you have 3 hours for it, but I'm planning to make it not much longer than any of the other finals, the other exams. So if you leave yourself 2 hours, that'll be plenty of time. I think there'll be people leaving by 1 hour and probably most people gone by an hour and a half. That's sort of my goal.